Hello everyone and welcome back to HealthGIS channel. Today we're diving into two of the most powerful epidemiological tools for controlling confounding variables. These methods are stratified analysis using the Mantel-Haenszel method and also modeling using logistic regression model. We will walk through a real outbreak dataset in our environment, explore the concept of confounding, compute adjusted estimates, and assess interaction, also known as effect modification. We will wrap up by comparing the results with logistic regression as another way to control confounding and interaction. Let's get started. So the story is on Saturday, April 21st, 1990, Gene Bateman hosted a luncheon for 45 guests, and many of them were epidemiologists from the London School of Hygiene and Tropical Medicine. By the next morning, Jean and her husband developed gastrointestinal symptoms, and soon after, more guests reported illness, raising concern about a foodborne outbreak. Our goal in this tutorial is to identify which food item was the likely source of the illness. Okay, so let's take a look at the data in Excel format. We have the data for 45 guests, and also we have information about whether they became ill 1 or 2. So the value that is 1 means that they developed illness, and 2 means that they didn't develop illness. And also we have information about their exposure and or what food they have consumed. The variables include items like cheese, crab dip, crisp, bread, chicken, rice, Caesar salad, tomato salad, ice cream, and so on. All variables have been coded as 1, which means that yes, they were exposed or they developed illness, or 2 or no, which means that they were not exposed or they did not develop illness. So let's start by loading the data into R. So in our environment, first of all, we use read.csv file.choose and set the header to true. And let's store it in an object, call it data. Okay, so run this line of code. It asks about where I have the data, and which is here, Gene Bateman, and then so here is the data. So you can look at the data here. So ill, cheese, crab dip, and so on, right? So let's take a summary of the data to see if there are any missing values or not, like the previous lab. So as you can see, all variables are complete, so there are no missing values. So now let's see how different food items are associated with illness. Like previous lab, we use EpiR package to examine crude association between food items and illness. So let's begin by examining the relationship between Caesar salad and illness by creating a 2x2 contingency table. So I create a table. So the first one is going to be your exposure, right? So from data, I'm going to select Caesar as my exposure, and also my outcome is illness. So I'm going to save this in an object called tab1 and then run. Now let's take a look at the table 1. So as here you can see, it seems like among the exposed, so these are exposed and these are the outcome. Among the exposed, most of them had Caesar salad. So in order to compute the odds ratio and relative risk, we use EpiR package like previous session, right? So library, I already have installed the EpiR package, otherwise you have to install it. But EpiR package, run. And then if you remember, we use epi 2x2 for the comment in order to calculate the variety of the statistics in EpiR package. So, and then the input is going to be table 1, run this line of code. And here are the results. Okay, so we have the exposed and the outcome. And also here is the risk ratio. As you can see, it is significant. The value of risk ratio is 3.91. And it is significant because it never crosses 1. And also, if you look at the odds ratio, it is very high. It's over 19, and also it is significant. So since both of them are significant, so there is a strong evidence and association between Caesar salad and illness. Okay, so let's do this for tomato, the association between tomato salad and illness. Okay, so I'm going to create another contingency table, table 2. So table is going to be between data of tomato, and also the first one is exposure, the second one is your outcome. And then, so this is table 2. And then we have to run the epi 2x2 for table 2, tab 2, and then run. And here also, as you can see, tomato salad is also significantly associated with illness. So if you look at the odds ratio is very high, never crosses 1, and risk ratio never crosses 1. So it implies that there is a strong, significant association between tomato salad and illness. Now the question is whether the tomato salad caused the illness or the relationship was confounded by Caesar salad. So let's test the relationship between tomato salad and Caesar salad first. Okay, so first let's look at this relationship. So I'm gonna create another table between Caesar salad and also tomato. Okay, so, and I'm gonna save this in tab 3, run. So since both of these are categorical variables, so if we want to investigate the relationship between two categorical variables, we use chi-square test, right? So chi-square for tab 3 and run. So as you can see, it's used the Yates contiguity correction for chi-square, and the values, the p-value is very, very small. So it suggests that there is a strong association between Caesar salad and tomato salad. All of these suggest that confounding is possible. Why? So first, let's review some basics about confounding to understand it. So what is a confounder? A confounder is a variable that distorts the relationship between exposure and outcome. A variable is a confounder if it is associated with exposure. Like here, confounder is associated with exposure. It is also associated with the outcome or illness, but it's not on the causal pathway between the exposure and outcome. Confounder cannot be here between exposure and the outcome. Okay, so in our case here, we saw that tomato, right? So we calculate the relative risk and odds ratio. The tomato is associated with Caesar, and also we found that tomato is associated with illness, and obviously tomato is not caused by Caesar. So tomato cannot be here. Tomato is not caused by Caesar. Okay, so it's not on a causal pathway. So tomato salad might be a confounder, and we will have to control for its effect. So there are multiple ways to control for confounding variables. In this session, we will talk about stratified analysis using Mantel-Haenszel method, and also modeling using logistic regression model or conditional logistic regression model. And in the next video, we will talk about matching techniques. Let's see how the Mantel-Haenszel works. So the Mantel-Haenszel is used when we want to adjust for a potential confounder using a stratified analysis. So instead of looking at just one big table, we break down the table into strata of the confounding variable and then calculate odds ratio or risk ratio within each stratum. For example, if tomato is a confounding variable, so Mantel-Haenszel calculates odds ratio for each stratum of the tomato among people who had tomato, and also calculates odds ratio relative risk for people who did not have tomato. And then Mantel-Haenszel method pulls this relative risk or odds ratio into a single weighted estimate known as the common or pooled odds ratio. So the larger stratum contributes more to the final estimate and the smaller stratum contributes less. And this combined number gives us a better, cleaner estimate of the true relationship between exposure and outcome, controlling for the confounder. So here we would like to examine the relationship between Caesar salad and illness, and controlling for confounding variable, which is tomato, right? So the table that we create here is going to be a three-dimensional table. So the first the first dimension is going to be your exposure, which is for our case is going to be Caesar salad, right? So Caesar is your exposure. And the outcome is illness. So the last one is going to be your confounding variable, which is tomato. Data is going to be tomato. So let's store this in an object table 4. And let's look at the table 4 to better understand it. It is going to be based on the strata of the tomato. It's going to be tomato is 1, and also tomato is 2, right? So when the tomato is 1, what is the relationship between the seizure and illness? And when the tomato is 2, what is the relationship between seizure and illness, right? So here, as you can see, we have larger number. So this one, the relationship or odds ratio that we calculate here, has higher contribution compared to this one. And then it combines it. It takes an average and gives you just one value, which is much cleaner than having multiple odds ratio. Okay, so now that I have table 4, I can easily just use the command Mantel-Haenszel So the input is going to be your table 4 and then run. So as you can see, we have a p-value which is significant, right? And so where is pooled odds ratio or common odds ratio? Is here. So common odds ratio is 12.5, and also the p-value is significant, right? We can conclude that the Caesar salad is still strongly associated with illness even after adjusting for tomato, right? So this confirms that Caesar salad is linked to the illness and is likely the real culprit even after adjusting for tomato salad. So now let's flip it. It seems like Caesar salad can be confounder in the relationship between tomato and illness, because Caesar salad was associated with illness. We calculated that. And Caesar salad was associated with the tomato that we calculated using the chi-square. And obviously, Caesar salad is not caused by tomato salad, right? So in order to investigate that, we have to again stratify the relationship between tomato and illness by Caesar, right? So it's going to be table, so I'm going to copy this. So it's going to be table 5. So the data here is going to be based on the tomato, the relationship between tomato and illness, but the confounder is going to be based on Caesar salad, right? So this is going to be table 5 and table 5. So let's look at the result. And so here is going to be the for the when they had Caesar salad, and among the people who did not have the Caesar salad, what's the relationship between tomato and illness? And here we'll have higher weight compared to this one. So when we combine it, this category will have higher weight compared to this category. Okay, so let's look at the results. So Mantel-Haenszel test, and for table 5. So as you can see here, the odds ratio is 2.05, but how about the p-value? The p-value, it is not significant, right? So the association between tomato and illness, disappears after controlling for Caesar salad as our confounder, okay? So tomato was just along for the ride and not the real culprit of causing the illness. Now let's talk about effect modification or interaction. So effect modification occurs when the effect of one variable on the outcome depends on the level of another variable. For example, does the effect of Caesar salad on illness change depending on whether the person drank wine or not? If yes, effect modification or interaction is present. And if there is interaction, it means the effect of Caesar salad on illness is not the same for the wine drinkers and not wine drinkers. So averaging across strata, like what we did for Mantel-Haenszel, would be misleading, and you should only report the results separately for wine drinkers and non-wine drinkers. But if not, if there is no interaction, the pooled odds ratio that you did for Mantel-Haenszel is valid. So before using a pooled estimate like Mantel-Haenszel odds ratio, we must assume that the association is consistent across levels of stratifying variables, for example here wine. So there are a variety of ways to test the interaction or effect modification, but the easiest one is using logistic regression. Why we are using logistic regression? So the biggest limitation of Mantel-Haenszel is that it can't handle continuous variables. And what if you have multiple confounders? It's not just one confounder. So in that case, logistic regression can easily address this issue. So last session, we learned how to run logistic regression. In our data, the exposures were coded as 1 or yes and 2 as no. So, but we need to recode them to binary values. If it's 1, it has to be yes. So yes is 1, but instead of 2, it has to be 0, okay? So 0 has to show the no. So for all dependent and independent variables. So we use the trick 2 minus data. So we use 2 minus data here. And again, saved it into variable data. So let's run this line of code and then now look at the data. So as you can see, all of the values that were 1 still unchanged because 2 minus 1 is 1, right? But if the value is 2, they now turned into 0 because 2 minus 2 is 0. So now we can fit a logistic regression model to test whether tomato remains significant after adjusting for Caesar salad. We learned how we can do that in previous session. Okay, so we use GLM and your dependent variable is gonna be, so data ill, right? And use tilde. So independent variable is gonna be Caesar, right? And plus tomato, right? And the family is binomial. So here also you could put data equals to data, but I already have done that. So let's run this line of code. And here are the results of the logistic regression. And so in order to see the results, so let's store it in variable, like for example, model 1, and then run, and then take a summary of the model 1. Okay, so here, as you can see, the tomato drops out. So this supports our earlier conclusion using the Mantel-Haenszel that the tomato salad was a confounder. Okay, so you can see using logistic regression is much easier, especially when you have multiple confounders, right? You can easily add the confounders here. But how about testing the interaction? For example, I would like to test the interaction between Caesar and wine. So in order to do that, so let's remove this one. We use multiplication. So that was the first one. So I would like to see or test the interaction or effect modification between this one and wine. Okay, so just this one, Caesar times wine. So, and if I run this line of code and then summary of that, so as you can see for wine times Caesar, the relationship, the p-value is, there is a weak evidence of interaction, okay? So in a small data set, this could still be important. But if p-value was less than 0.05, we would say the effect of Caesar salad depends on wine consumption. This means that we should avoid using a single odds ratio to summarize the effect. And instead, we have to report the association separately depending on wine consumption. So in conclusion, crude associations can be misleading due to confounding. Mantel-Haenszel provides adjusted estimate across strata. You have to always check for interaction before interpreting pooled effects. And logistic regression is a flexible tool for both confounding and interaction.